Dear students, today we are in lecture number 12. So up to lecture number 11, we have discussed the properties of concrete, what are the various properties of concrete and how they will be helpful in designing any RCC structure. Then we have discussed the limit state methodology, that means various parameters, various provisions in the limit state design in case of with the help of IS 456 2000. And then we have in detail analyzed various type of singly reinforced section and what are the various design considerations which we have to keep in mind and we have to take into consideration while analyzing any singly reinforced beam section. So now today we are going to discuss in lecture number 12, that is doubly reinforced section. That means in doubly reinforced section we will be using steel as a tensile member as well as in a compression side we will be providing the steel. Now let us go through the basic guidelines. In earlier in singly reinforced section we have studied in detail about the Engg guidelines in Engg G regarding the movement of a resistance of a rectangular section, and we were able to calculate limiting moment of a resistance by referring various formulas given in Engg G of IS 456. So you have came across this type of formula, that is mu limiter is equal to 0.36 xu max, that is xu max mean limiting value of depth of the neutral axis, and here small d was the effective depth of the section and fck is the grade of the concrete, that means it is the characteristic compressive strength based on the grade of the concrete. So till this we are able to understand and do the calculation regarding finding the ultimate moment of resistance as well as limiting moment of resistance, which is restricted by IS 456. Now if we analyze very carefully this formula, that means what are the various factors, what are the various values which we are using or taking the help of the various values in the calculation of limiting moment of resistance. So if we just rewrite this equation in this form, now you will be able to understand that is formula will be in the form of xu max raised to power 2 and multiply by width of the section as well as the characteristic compressive strength of the concrete. So from the formula it is very much clear that if you want to increase the moment of resistance of a section, either you can change the dimensions of the section or you can increase or take the higher grade of concrete in the casting. So prominently we can increase the size of the section, that means you can increase the depth of the section as well as other dimensions. Now we can increase the size of section, that is depth, if all other parameters are to keep fixed. That means if you have decided that a particular grade of concrete is taken and a particular width of the section is taken, that means width of the section is fixed, grade of the concrete is finalized, but still you want to just increase the ultimate moment of resistance of the section, then very prominent value is you can change the depth of the section. If you increase the depth of the section, so definitely this first part of the equation will increase and the second part will not be more affected. So if xu max value is fixed and the based on the value of d, So very as in simple language we can say, if you want to increase the ultimate or limiting moment of a resistance of the section, you can increase the depth of the section. But again, it does not mean that you can increase the depth of section as per your choice, because again code is restricting the depth of section. Later on we will be going through that guideline more clearly. No, but very important aspect is, in case of any architecture requirement, suppose the design which you are going to be uh, taking into consideration, that means you are going to design any structure, but if the architect or the planner has restricted the depth of the beam, so that means if the depth of beam is also restricted and the other parameter you don't vary, because V and D ratio we have to keep as per the based on the experience, you can say. That means you have to basically proportionate D by B ratio, which I will be going to discuss later on when we will be going deep into the design. So here what we have to understand, that if the depth of the beam is restricted, so it means you will be unable to increase the limiting moment of a resistance. Then what we will be going to do, then what will be the options which we are having in our hand? Either you can increase the grade of concrete or you can increase the width of the section. So now here, if I say in that depth as well as width, if both are restricted, then what you will do? Then you have only one option, that is you can increase the grade of concrete. But grade of concrete will not affect so much that it will be increasing the ultimate or limiting moment of resistance considerably. Because if you take the higher grade, suppose you are taking M20 grade, then FCK will be 20 MPa, and if you take M30 grade of concrete, then it will be only increased by 10 MPa. So in general construction practices, we don't take any higher grade, that means high strength concrete, which are generally considered more than 50 MPa, that means M50. So what I want to say here, that depth is restricted, width is restricted, as well as grade of concrete is also restricted, because if you go for the higher grade of concrete, then it has its own complications. That mean more efficient mixed design you need to do, as well as more efficient you can say labor, as well as the persons required at the site will be more expensive, you can say. That means you need more skilled type of labor here. So what we want to discuss, that means if these are the some of the restrictions imposed in front of the designer, then the beam has to carry moment greater than the limiting moment of moment capacity of the beam. Then what is the option with the designer? So in such type of cases where higher bending moment need to be taken care by beam sections with the limited depth, then the sections are designed to have both tension as well as compression reinforcement. That means we will be providing reinforcement in tension zone as well as compression zone. Or in other sense we can say, now the steel will be taking care of compressive stresses as well as tensile stresses, along with the concrete which will be able to take compressive stresses. So these type of beams or these type of sections are known as doubly reinforced beams. Now compression reinforcement, that means reinforcement which we are going to provide in compression zone. In a simply supported beam, you can say above the neutral axis we have to provide steel also, and that will be in the compression zone, along with the steel which we are providing below the neutral axis, that is in the tension zone. So compression reinforcement in compression zone is to be provided in addition to the tension reinforcement. Now you can see a section diagram here where you can easily see here that two type of reinforcement are provided. This yellow color is tensile reinforcement, and this dark color, that means brownish color, or you can say gray color, this reinforcement is the compression reinforcement. So in this section what we are doing, we are providing reinforcement in tension as well as compression in both the zones. So that's why we will be saying that this beam we have to design as a doubly reinforced section. Now this type of sections, or doubly reinforced type of sections, are suitable in the section where tension steel is more than the limiting area of the steel recommended by the code. That means if you are going to design and you are getting tensile steel, that means you are calculating area of tensile steel, but that area is also restricted because IS 456 also restrict the higher limit of the tensile steel. Otherwise, there will be another type of failure. That means it may be over reinforced type of failure. So that's why code is restricting the tension area also. But if in our calculation tensile steel required is more than the limiting area of steel recommended by code, then we have the option to provide the steel in compression as well as tension both zones. Now compression steel may change the mode of failure from compression failure of concrete to tension failure of steel. It may even change the section from over reinforced to under reinforced. Now compression steel, in addition to increasing the resisting moment, also increase the amount of curvature that a beam member can take before failure in flexure. So it has their own advantage in case of curvature, that means in case of a deflection criteria. Moreover, the ductility of section is also increased by providing doubly reinforced section. And the compression steel is also effective in reducing the long-term deflection, which may be due to shrinkage as well as creep. So here are few of the advantages of providing steel in the compression zone along with the tensile zone. Now let us just recall the assumptions which we have mentioned in clause 38 of IS 456. Earlier we have gone through very carefully. We have discussed all the assumptions in case of RCC beams. Now here we have to understand this diagram more carefully. So we will be, first of all, we will be going through the diagram, that is the sectional diagram. Here in this sectional diagram, uh, this is a rectangular RCC beam having width B as well as effective depth D. So effective depth we are taking from the outermost compression fiber to the center line of the reinforcement in the tension zone. So whatever the steel you are providing here, that will be covered under area AST, that means area of steel in tension zone. And again we are providing some reinforcement, which later on you will be able to understand more effectively when we will be directly designing singly reinforced as well as doubly reinforced section. So let us first of all understand what is the analysis of the singly reinforced and doubly reinforced. So here when we are providing steel in the compression zone, so we are naming it as ASC, that means area of steel in the compression zone, or you can say area of steel that is taking compressive stresses. So topmost fiber to the center of the compression steel, we are writing it as D dash, and this will be the strain diagram. So strain diagram will not be affected. That will be similar to singly reinforced section. Here at the bottom you can see strain, that is epsilon st, strain in steel in tension zone. And this epsilon cu, you are well aware, this is the ultimate strain in concrete, that is 0.0035 as per the IS 456 according to limit state methodology. Now you can see here this red color line, that is at the level of the compression steel. So we can calculate from these two similar triangles what will be the strain in the steel in compression. So here epsilon SC we can calculate from this triangle with the help of triangle law. Now there will not be any change in the XU value. That means XU will be the depth of the neutral axis at the ultimate limit state, that is distance from the topmost fiber to the neutral axis. But only difference here is that this will be d minus XU, and another new thing which we are going to discuss here, that is d dash. D dash is the distance of the compression steel bars from the outermost or topmost compression fiber. So you can see here, this is the strain due to compression in concrete, this is the strain in compressive steel, and this is the strain in tensile steel. Now third diagram is the stress diagram, which we are going to discuss now. At the level of tensile steel, the stress level is, or stress value is 0.87 Fy, as we have discussed in the previous singly reinforced also. Now only there is small difference you can see here. At the topmost level, this is the 0.447 FCK. This is the stress at topmost compression fiber in case of concrete. But now we have provided steel also in the compression zone. So here FSC will be the compressive stresses in case of steel in the compression zone. So only new term is this FSC. So let us go one by one. AST is the area of tensile steel. ASC is area of compression steel. Epsilon SC strain at the level of compression steel. So that we are we have discussed. And FSC is stress in the compression steel. Now we have to understand this diagram more effectively and more carefully, that is the resultant force. Now at the level of steel, if we start from the bottom, at the level of steel, Tu is the force in the tensile reinforcement at ultimate limit state. Now here you have to understand these two values. One is CUS. So what is a CUS? CUS is the compressive force in the compression steel. So that will be the compressive force which you can calculate by multiplying FSC with ASC, where FSC is the stress in the steel in compression and ASC is the area of the steel which we have provided in the compression zone. Now another term is CUC. Now please understand it more clearly. What is the meaning of CUC? Here C mean that is the compressive force at ultimate limit state in concrete. So that is compressive force in concrete. But here another thing which we have discussed that we have to keep in mind, that means it is the compressive force in concrete, but we have to exclude the area of the concrete which is replaced by steel, because here when you provide compression steel, that means some area of the concrete you have removed. So that area which we have removed, that will be equal to area of the compression steel that we have to exclude from the calculation. So what is CUC? CUC is the compressive force taken by concrete And what is the area of concrete? Only you have to exclude the area which is covered by steel bar in case of compression steel. So this we have discussed in the previous section, that CUC you can calculate like this. Here now lever arm, if you say lever arm between CUS and TU, that is D minus D dash, and the rest is same in the, as we have discussed in the singly reinforced, D minus 0.416 XU. Now again, according to force equilibrium, that means total compressive forces will be equal to total tensile forces, so that the beam section should remain in equilibrium. So we can say, as we discussed, the total compressive force is equal to total tensile force. Now total tensile force is taken by this AST, and total compressive force is taken by ASC, that is area in the compression steel, plus force, compressive force taken by concrete above the neutral axis, excluding the area of compression steel which it has been covered by the compression steel. So we can just write it as, this is CUS plus CUC which we have discussed, that is force taken by steel, as well as this is the compressive force, that is equal to total tensile force which is taken care by steel at the bottom, or you can say in the tension zone. Now CUC is taken by 0.36 FCK BX. This is the formula which we are already aware. Now CUS, here is the twist we can say. Now this is FSC into ASC. This is the force taken by, that means compressive force taken by compression steel. Now minus this much. Now what is this? This ASC here, it is the area of the compression steel, but we are taking here compressive stress. That means this parameter, this factor 0.447 FCK, we are just assuming that as in the topmost compression fiber, compressive stress is 0.447 FCK, and we are ignoring this small area, so that we are assuming that compressive force at the level of steel due to concrete, which we have excluded, which we have removed, so that much compressive force which that concrete can take, now it will not take because we have removed it. So that's why net force is reduced by this factor 0.447 FCK, that is ASC, area of concrete which you have removed, and automatically that will be equal to ASC, area of concrete which you have removed from the section in the compression side, that is equal to area of steel. So just combining this these two equations, two part of equation as a one equation, that is FSC minus 0.447 FCK, and taking out ASC outside. Now assuming, as already I have discussed, that assuming same value of compressive stresses at the level of compression steel for simplicity and for making the calculation easy, and TU, you are well aware that this TU is equal to FST into AST, and FST we have taken 0.87 FY, and AST is area of the steel in the tension zone. Now from these 3-4 equations, that is this equation number 1, 2, 3 and 4, solving all these equations, you will get the formula for depth of the neutral axis. So this is given by FST AST minus FSC minus 0.447, which we have taken from here, and this. Now you are, if you analyze this equation, you can easily understand that XU value depend upon grade of concrete, stress in steel at the level of concrete, stress in steel at the level of tension steel, and grade of concrete again, as well as width of the section. Now here what we are just assuming one thing, that means we are considering that stress in steel in tension as well as stress in steel in compression, that is equal to 0.87 Fy. So again, for the simplification of the calculation, we are taking this value. Otherwise, we have to do the iteration method. But in actual, we can say that FSC and FST depend upon the value of XU. That means what is the value of XU on these FSC and FST value depend. So now how to calculate movement of a resistance? Now you can, I think you are able to understand that ultimate movement of a resistance section can be calculated by taking the moment of both CUS and CUC. That means ultimate movement due to force in steel in compression as well as force in concrete in compression. And you can take the moment about the center line of the tension steel. So that's why lever arm will be changing. Now MUR is the ultimate moment of resistance, that is CUS. CUS is acting at this level. So lever arm of this force from 0.87 Fy, that it is D minus D dash, and plus CUC. What is CUC? 0.36 FCKBXU, and lever arm of this force with respect to TU is T minus 0.416 XU, which you are already aware about it. So solving this equation by putting value of CUS and CUC, which we have taken here as well as in the previous slide. So equation for the movement, that means ultimate movement of resistance, is worked out to be this equation where we have incorporated all the parameters. And if you are willing to find out, then we, as per codal restriction, what will be the limiting moment of resistance, we have to only substitute XU max instead of XU. So you can put the value of XU max instead of XU. And you are now already aware that MUR value should be less than MU limited for the safety of the section as well as by following the guideline of IS 456, which are mentioned in lecture G. So in the next lecture, we will be able to design either singly reinforced section or some more information related to doubly reinforced section. Thank you.